Right now, far beyond Mars, an object from another star is breaking almost every rule we teach about how comets behave. Its tail points the wrong way. Its chemistry does things textbooks say should not happen. Its path through our solar system has a natural probability of just a few tenths of 1%. In a matter of days, it will skim past the sun and either shatter like dirty ice or glide through untouched. If it survives, we may have to rethink what we believe about interstellar visitors. We are living this story in real time, together. So settle in, stay with me to the end, and tap like and subscribe so you do not miss what happens next. Let us start with the basics. 3I Atlas is an interstellar object, which means it came from beyond our solar system entirely. It has been traveling for billions of years through the dark between stars, older than our sun itself. Now, it is plunging inward on a steep, retrograde path, moving opposite the direction of the planets, at more than 200,000 kilometers per hour. At the moment described in this story, it is roughly 350 million kilometers away, rushing toward a close brush with the sun. That alone would make it interesting. But that is not why scientists are losing sleep. To understand the problem, picture a normal comet. A comet is basically a frozen relic from the early days of a planetary system, a mix of ice, rock, and dust. When a comet falls inward toward its star, sunlight heats the surface. Ice turns straight into gas and jets into space. Solar radiation and the solar wind then sweep that gas and dust away, creating tails that stream out in the direction opposite the star. Tail points away from sun. That is Comet Physics 100. 3I Atlas looked like it would follow the same script. Then the telescope started to notice things that did not fit. On images from the Twin Telescope in the Canary Islands, astronomers saw a narrow streak of material, almost 6 kilometers long, pointing not away from the sun but toward it. This is the anti-tail that has become famous, a feature so counterintuitive that many comet specialists simply waved it away as an odd viewing angle. At the same time, spectroscopic measurements hinted that the object was venting nickel in the gas, without the usual companion iron, which should not be possible if the metals were mixed in natural rock. Enter Avi Loeb, the Harvard astronomer who became widely known during the debates over the first interstellar visitor, Oumuamua. Looking at the early data on 3I Atlas, Loeb calculated that the particular path this object took into the inner solar system has a natural probability around 0.2%. Not impossible, but very unlikely. Combine that with the strange tail geometry, the odd metal ratios, the unusual brightness and color, and he sees a pattern. Each anomaly on its own could be noise or error. All of them together start to look like a message that our current models are missing something important. Officially, NASA and other major institutions reject any talk of technology. They classify 3I Atlas as a natural interstellar comet, exceptional but still within the broad family of icy bodies we already know. That cautious stance is not unreasonable. Science is built on skepticism. Extraordinary claims require extraordinary evidence. Most anomalies in history have quietly evaporated once better data arrived. So the default position is simple. Until something truly undeniable appears, treat this as a strange but natural rock and ice fragment from a very old, very alien star system. Yet there is also a deeper tension here. Scientific institutions are designed to be conservative. They protect the core models that explain most of what we see. They update slowly, and only when the evidence is overwhelming. That is how they avoid chasing every mirage. But it also means that when reality really is doing something new, the first reaction is often to force the data into old boxes and to dismiss details that do not fit. 3I Atlas now sits right on that line where healthy skepticism and willful blindness can look uncomfortably similar. Everything now comes down to what happens near the sun. On the date of perihelion, when 3I Atlas reaches its closest approach, the object will be hammered by intense heat and radiation. A typical comet would flare brighter as more ice vaporizes, grow long sweeping tails, then either lose huge amounts of mass or crack apart entirely. 3I Atlas might do exactly that. If it fragments into a cloud of rubble, the story probably ends there. Weird, yes, but still a comet. If it does not, If it sails through the worst of the heat and solar wind as a single, stable body, then the natural explanation suddenly has a much harder hill to climb. At the same time, geometry works against us. During this critical window, the object moves behind the Sun from Earth's point of view. Our best ground-based telescopes are effectively blind. Space-based instruments get only narrow viewing angles and short observation windows. It is as if the universe chose the one part of the orbit where we have the worst possible vantage point to run the most important experiment. For people like Loeb, who already suspect intentional design, that timing looks almost too convenient. For cautious dynamicists, it is just an annoying coincidence of orbital mechanics. Either way, you and I are watching a real-time experiment at the edge of current knowledge. The first interstellar object slipped past before we could really study it. The second was more cooperative and looked comfortingly familiar. 3I Atlas is the first one we have seen coming early, with months to prepare, and it refuses to behave in a way that lets everyone relax. In the next part, we will dive deeper into the most visually shocking clue of all, the tail that points straight back at the star, and why that single image has become the central symbol of this entire mystery. The first time astronomers really stared at the detailed images of 3I Atlas, what grabbed them was not the brightness or the color. It was a single thin streak of material pointing the wrong way. Instead of streaming outward, away from the glare of the sun, this feature was aimed almost straight back at it. In the raw data from the twin telescope in the Canary Islands, you see a narrow dagger-like line a few miles long, anchored on the object and aimed sunward. That one picture is why people started using a new phrase for it, the anti-tail. To understand why that is such a big deal, we need to slow down and talk about how comet tails actually form. A comet is a dirty ice ball falling inward. Sunlight heats its surface, ices turn into gas, and jets of vapor and dust spray into space. That outflow by itself can go in many directions depending on where the vents are, but once the material leaves the comet, the solar wind takes over. The solar wind is a constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second. It acts like a cosmic hairdryer, blasting gas and dust away so that the main tails point roughly opposite the star. Most comets have two main tails. A dust tail, made of heavier particles, bends gently along the orbit, like smoke caught in a breeze. And an ion tail, made of ionized gas, which points more directly away from the sun, pushed straight back by the solar wind. The exact shapes can be messy, but the basic rule holds. Tails do not naturally line up like spears pointing inward. Gravity pulls toward the star, light and wind push away from it. The tails trace the push, not the pull. There is a known optical trick in comet astronomy that sometimes produces something which looks like a sunward spike. When Earth crosses the orbital plane of a comet, dust that was left behind along the orbit can appear as a narrow structure that seems to point toward the sun. In reality, it is a sheet of particles seen edge-on, stretched along the path of the comet, not a jet literally firing into the star. Many so-called anti-tails are really this perspective illusion. If that were the whole story, 3I Atlas would not be controversial. We would simply file it under strange but understood geometry. The problem, Avi Loeb and a few others argue, is that this particular feature does not line up neatly with that explanation. In the Canary Islands data, the anti-tail is not just a faint extension of the orbit. It is bright, compact, and appears to be aligned almost exactly along the sunward direction in the sky at that time. When modelers try to reproduce it using normal dust dynamics and viewing angles, they can get something similar, but not quite as sharp or as perfectly pointed. The more precisely you measure it, the more it looks like material being directed, not just passively blown around. Think about what that would mean. For a comet to maintain a stable, sunward pointing structure, the stuff coming off it would have to be launched in a very specific direction and with enough speed that the solar wind does not completely reverse it. You can imagine powerful jets on the night side, angled back toward the star, firing constantly as the object rotates, but that requires a very particular alignment of vents and spin. It is not impossible in a natural body, but it demands a lot of coincidence. Most comet specialists are not impressed by that argument. They point out that small changes in assumed orbit, dust size, and viewing geometry can dramatically alter the model images. When they run simulations with realistic parameters, anti-tail-like features do appear. From this perspective, 3i Atlas is a case study in how our brains latch onto the most dramatic interpretation of a picture and ignore the boring math behind it. A neat sunward spike feels like a thruster plume. A dusty orbital, sheet seen edge-on feels dull. Human pattern recognition prefers the exciting option. Loeb looks at the same data and sees something else. For him, the anti-tail is one piece of a larger jigsaw. On its own, yes, it could be geometry. But stack it together with the nickel-rich outgassing, the near absence of iron in those same spectra, the strange water vapor levels at large distance, and the improbably flat, retrograde orbit, and he argues that you no longer have one illusion. You have a pattern, and patterns, in his view, are what you expect from engineering. Natural systems can be weird, but they rarely line up all their weirdness in one place. It is important to be honest about the limits of what an image can tell us. A single photograph cannot prove the presence of engines, no matter how much the tail resembles a rocket exhaust in a science fiction film. The resolution is low, the processing is complex. Scattered light, noise, and background stars can all trick us. At the same time, dismissing the feature entirely because it would be inconvenient if it were real is just as unscientific. The proper response is neither automatic belief nor automatic denial. It is to treat the anti-tail as a clue and to test every possible natural model against it as rigorously as we can. Whatever it turns out to be, this sunward streak matters because it forces us to confront how deeply we trust our models. For decades, comet physics has been a comfortable field. There are surprises, but the big picture is stable. Tails point away from the sun. Activity turns on at certain distances. Composition stays within familiar ranges. 3i Atlas has walked straight through those expectations and painted a bright line across the sky that says, maybe not. In the next part, we move from shape to chemistry. If the tail direction hints at strange forces, the molecules in that tail reveal the environment where this object was born, and possibly how it has been altered. And the numbers, they're even stranger than the geometry. So far we have talked about what 3i Atlas looks like. Now we get into what it is made of, and that is where things become truly unsettling. When astronomers pointed sensitive instruments at this visitor, they did not just see ice and dust, they saw water pouring off an object that should still be frozen solid. They saw a comet whose breath is made mostly of carbon dioxide instead of water. They saw metal-rich gas that seems to carry nickel but almost no iron. Put that together, and you do not just get a weird comet. You get a chemical fingerprint from a place that does not look like our solar system at all. Let us start with the water. Using a space telescope designed to study energetic events, researchers measured the amount of water vapor streaming away from 3i Atlas. The number they got was around 40 kilograms every second. Imagine 40 large bottles of water turning straight into vapor every heartbeat. That is, thousands of liters per minute. For a normal comet closer to the sun, that would be impressive but not shocking. Far out where this measurement was made, it should be almost impossible. At roughly 3 astronomical units, about 3 times farther from the sun than Earth, sunlight is faint. The energy that reaches any object out there is only a small fraction of what we receive. It is enough to warm a surface a little, but not enough to boil ice furiously into space. Most comets do not really wake up until they cross inside 2 astronomical units. They become dramatically active, closer still, inside about 1.5 astronomical units. 3i Atlas is behaving as if it is already in that inner zone, while still cruising near the asteroid belt. You can picture a snowball sitting in a weak beam of light, yet somehow giving off a thick, steady mist, as if it were held over a campfire. The math does not close. The energy coming in from the star is not enough to explain the energy, going out in the form of water vapor. Something else has to be providing the power. One idea is that the heat is coming from inside. Maybe 3i Atlas carries radioactive elements that slowly decay and release energy, warming the core and driving outgassing from below the surface. That is not crazy. Some moons and asteroids are heated in part this way. The problem is time. If this object is 7 to 10 billion years old, as some models suggest, most of the short-lived radioactive isotopes are long gone. Only the very longest-lived elements are still decaying, and their heat output is tiny, enough to nudge temperatures, but not to power a constant fountain of water on the scale we are seeing. Another natural explanation leans on exotic ices. Perhaps 3I Atlas is rich in substances that vaporize at very low temperatures. Think of ingredients so volatile that they start evaporating as soon as they feel the slightest warmth. That could, in theory, drive strong activity, even far from the sun. But when scientists look at the spectrum, the light split into its chemical colors, they do not see clear evidence of some new ultra-volatile ingredient in huge amounts. They see something stranger. The ratio of carbon dioxide to water is upside down. In most comets from our own system, water is the main component. Carbon dioxide and carbon monoxide show up, but water dominates. In 3I Atlas, the measurements suggest roughly 8 parts carbon dioxide for every 1 part water. That is not just a tweak. It is a completely different recipe. It tells us that the cloud of gas and dust that formed this body had abundant carbon and oxygen, but relatively little hydrogen available to make water ice. In simple terms, that means it was born under a different kind of star. The exact details are still debated, but the message is clear. This is material from an environment where the balance of elements was not the same as the balance that built our planets and comets. 3I Atlas is a messenger carrying the chemistry of another sun right through the middle of our sky. Now add the metals. Spectroscopic studies show emission lines from nickel in the gas streaming off the object, with little or no matching signal from iron. In cosmic chemistry, nickel and iron are inseparable partners. They are forged together in the hearts of stars and in supernova blasts. Rocks and dust grains usually hold both. If you heat and vaporize that dust in a natural way, you expect to see both metals in the gas. Nickel, all by itself, is like finding only one twin at a family reunion. Even more intriguing is the possible detection of a molecule called nickel tetracarbonyl. On Earth, this compound appears mostly in industrial settings. It forms when metallic nickel reacts with carbon monoxide gas at specific temperatures and pressures. It is used to refine nickel in chemical plants. It is volatile, toxic, and touchy about the conditions it needs. Spotting it in space around an interstellar comet is profoundly odd. To get this molecule around 3I Atlas, you need several things. You need metallic nickel, not just nickel locked inside stone. You need plenty of carbon monoxide in the gas surrounding it. You need the right thermal environment to drive the reaction. That is a very particular setup. Maybe some exotic process in the birth cloud produced free nickel grains that later reacted in the coma. Maybe impacts or heating freed nickel from rock and let it combine with carbon monoxide in just the right way. Natural explanations are possible, but each one piles more special conditions onto an already unlikely story. There is another way to read it, the way Avi Loeb suggests. If you imagine 3I Atlas not as a simple lump of primitive ice, but as something that has been processed, perhaps even engineered, then nickel without iron and chemical species like nickel tetracarbonyl start to look like the waste stream of a refinery. In that picture, some mechanism inside the object separates metals, uses or stores iron, and vents nickel-rich compounds as byproducts. The carbon dioxide-heavy mixture could be coolant or exhaust rather than untouched primordial ice. That does not mean we should jump straight to the word artificial, but it does mean the chemistry alone would justify calling this object the strangest interstellar visitor we have ever seen. It is hyperactive in the cold. It breathes mostly carbon dioxide instead of water. It coughs up nickel in ways that defy simple mineral physics. Its composition points to a parent star and a planetary system very different from our own, and maybe to a long history of internal processing that we do not yet understand. In the next part, we will step back from the molecules and return to the path this thing is taking through our neighborhood. Because when you combine a bizarre chemical fingerprint with an almost impossibly well-placed orbit, the question of who or what set this course becomes impossible to avoid. Imagine you are an interstellar rock drifting in from deep space. From your point of view, the solar system is a tiny moving target. The sun is a bright dot. The planets are grains of sand, orbiting in a thin, spinning disk. Out of all the possible paths you could take, you would expect to blast straight through on some steep, random angle, never coming close to anything. That is what most orbital models say should happen. 3i Atlas did something very different. It threaded the needle. When astronomers reconstructed its orbit, two details jumped out. First, it is retrograde. It moves around the Sun in the opposite direction to the planets. Second, its path lies only a few degrees off the plane of the solar system. That plane is called the ecliptic, the thin sheet in which almost all planets and most asteroids travel. Statistically, an interstellar visitor should come in from above or below that sheet at a sharp angle. There is simply more volume in those directions. Hitting a retrograde track that is only about 5 degrees off the plane is, by some estimates, a 0.2% outcome. Think of all possible trajectories as a giant sphere surrounding the solar system. Most of that sphere corresponds to high inclination entries, where an object dives in from the galactic background and exits again, without ever lining up with the orbits of Earth, Venus, Mars, or Jupiter. 3i Atlas came in almost exactly along the disk, where all the interesting stuff lives, but going the wrong way around. That is exactly the kind of path you would pick if you wanted a slow, detailed flyby of the inner planets rather than a quick, distant pass. Now add speed. When this object crossed the boundary of the inner solar system, it was moving at around 210,000 kilometers per hour relative to the Sun. That is fast, but normal for interstellar debris. As it falls inward, gravity from the Sun pulls harder, accelerating it. Near perihelion, at about 0.89 astronomical units, just inside the orbit of Earth and roughly similar to the orbit of Venus, it will be moving at over 300,000 kilometers per hour. That huge swing in speed is exactly what you expect from a body falling through a deep gravitational well. Here is where things get interesting. If you were designing a probe to use the Sun as a slingshot, this is almost the perfect path. A low inclination orbit keeps you in the same plane as the planets, giving maximum chances to observe or use their gravity in the future. A retrograde track maximizes relative velocity for certain kinds of science and gives a distinctive geometry for interactions. Skimming inside Earth distance, but not too close, avoids extreme tidal forces while still tapping a strong gravitational assist. And choosing a perihelion that happens behind the Sun from Earth's perspective hides any subtle maneuvers inside the glare. Astronomers have noticed tiny variations in the velocity of 3i Atlas as it moves inward. The standard explanation is outgassing. When jets of gas and dust blast off a comet, they act like small thrusters, giving the nucleus a gentle push. If those jets are not perfectly balanced, they can speed the object up a little or slow it down along its track. For a natural comet, that is normal. For an interstellar object, it is still normal, as long as the magnitudes and directions match what the observed jets can produce. So far, the reported deviations for 3i Atlas are small, hovering near the limits of measurement error. Most dynamicists consider them unremarkable. Yet when you overlay the orbit on the solar system, you see a path that seems to dance between deeper gravitational wells without major detours. It passes within range of Venus, Mars, and Jupiter's extended influence, but does not get yanked into a dramatically different course. The perturbations are there, but they appear to cancel out enough that the overall track remains elegantly smooth. One way to picture this is the three-body problem. When you have a sun, a planet, and a small object, their combined gravity creates a complex field of pushes and pulls. Most paths through that field are chaotic. Small changes in the starting point lead to very different outcomes. Finding trajectories that weave past multiple planets without large deflections is like trying to throw a ball through several spinning fans and having it pass cleanly between the blades every time. Nature can do it by chance. So can careful calculation. Critics of the artificial hypothesis point out that we only notice the neatness of the path after the fact. Out of all the random interstellar objects that might enter the solar system, we are far more likely to pay attention to the ones that just happen to come close to the planetary plane and near Earth. That is a selection effect. If 3i Atlas had plunged in at a steep angle, well away from everything, we might never have discovered it at all. In that sense, The orbit is only surprising because we are here to see it. Supporters of the navigated scenario respond that the combination still matters. A low inclination, retrograde track that arrives during a period of intense interest in unidentified aerial and space phenomena that happens to skim near multiple worlds, and that reaches maximum stress where most of our instruments are naturally blind, looks less like a random throw and more like a planned survey pass. They see intent where others see coincidence. There is another subtlety here. At perihelion, when the object is closest to the Sun and moving fastest, any active maneuver it performs will be hardest to distinguish from natural gravitational effects. If some internal system fires thrusters to change speed or direction slightly, that change will ride on top of the huge acceleration already provided by the star. Observers on Earth, working with limited angles and noisy data, might easily attribute everything they see to gravity and outgassing. If you wanted to hide course corrections, you would do them exactly there. From the standpoint of pure celestial mechanics, the orbit of 3I Atlas can be described entirely with classical physics. Gravity works. The equations integrate. The path can be extrapolated into the distant future as it leaves the solar system behind and returns to the interstellar dark. That is the safe story. Yet when you step back and look at the geometry through the eyes of a mission designer rather than a disinterested rock, the picture changes. You see a trajectory that offers maximum scientific return with minimal risk and maximum stealth. In the next part, we will leave the chalkboard and return to physical reality near the Sun. Because soon, the question will not only be which path 3I Atlas takes, but whether it survives the journey at all. What happens to this object at perihelion is the simplest, hardest test of every model we have built so far. Every comet that dives toward a star faces the same final exam. Heat, radiation, and tidal forces all ramp up together. Some stagger through, scarred but intact. Others fail spectacularly, brightening for a moment and then tearing themselves apart into a spray of rubble. 3I Atlas is rushing toward that same trial by fire. What happens in that narrow window around closest approach may be the most important single piece of evidence we ever get about what this object really is. To see why, picture the inside of a typical comet. It is not a solid crystal of ice. It is more like a frozen junkyard. Dirty snow, rock fragments, dust, and pockets of more volatile ice are loosely glued together by weak forces. There are cavities and cracks everywhere. As the comet approaches the Sun, the outer layers warm. Ices in those cracks flash into gas, building pressure from within. At the same time, the surface is shedding material into space, peeling away like layers of an onion. That combination makes comets fragile. When internal pressure grows faster than the structure can vent it, the whole thing splits. We have watched this many times. Comets have blown themselves into chains of glowing fragments. Others have simply faded after disintegrating into dust, too fine to reflect much sunlight. In many cases, the timing is predictable, close enough to the star, for long enough, and the weak glue can no longer hold. 3I Atlas is already throwing off mass at a serious rate. The 40 kilograms of water vapor per second we talked about earlier is only part of the story. Add in carbon dioxide, carbon monoxide, dust, and those nickel-bearing gases, and the total mass loss may be 50 or 60 kilograms every second. That is more than 5,000 kilograms per day, roughly 150,000 kilograms per month, and the rate is increasing as it falls inward. By the time it swings past the Sun and begins the climb back out, it could have shed several million kilograms of material. Whether that matters depends on how big and how dense the nucleus really is. If 3I Atlas is 6 kilometers across and has a comet-like density, its mass could be tens of trillions of kilograms. Losing a few million kilograms would barely scratch it. If it is smaller, closer to 2 kilometers across, and the same mass loss continues or spikes around perihelion, the fraction of total mass removed becomes more significant. In that case, the stress from gas pushing through internal fractures might be enough to crack the body apart. Some researchers have suggested that 3I Atlas might not be a single solid nucleus at all, but a kind of ancient debris field. In this view, it is a loose swarm of fragments held together by mutual gravity. something like the rubble pile asteroids we know in our own system. Different pieces could carry different compositions, which might help explain the strange mix of gases. Separate fragments could also vent in different directions, creating complex tails and perhaps even features like the anti-tail without needing any exotic physics. On paper, that idea is attractive. It stays inside the boundaries of natural processes while still giving room for messy behavior. In practice, it raises its own puzzles. Rubble piles are not eternally stable. Over billions of years, passing stars, giant molecular clouds, and gravitational nudges from other planets and objects gradually tug at them. Fragments drift. Loose clusters spread out. The more times a rubble pile passes near stars, the more likely it is to be shredded into an elongated stream of debris rather than a compact object. For 3I Atlas to survive 7 or more billion years as a tight debris field, either it has experienced a remarkably gentle history, or something has kept it more cohesive than a typical pile of rocks and ice. There is also the chemistry. The rubble pile might naturally mix regions of different composition, but it does not obviously solve the nickel without iron problem or the potential presence of industrial-style nickel compounds. Those are questions about how the material was processed, not just how it was stacked. Breaking the nucleus into fragments does not make that chemical imbalance easier to explain. This is why fragmentation at perihelion is such a clean test. Comets fragment because they are weak. They fragment because they are porous, low-density bodies held together by nothing more than cold and a little gravity. When they survive extreme heating, it is usually because they never got quite close enough for the stress to exceed their structural limits. 3I Atlas is going close enough that the limits will be probed in full. If it breaks into pieces, the conservative story wins. We will be able to say, with some confidence, that whatever its weird chemistry and odd trajectory, this object shares the same basic architecture as many other comets: dirty ice, weak cohesion, thermal cracking. The anomalies will be reinterpreted as rare but still natural variations inside that broad class. The debate over artificial origin will shrink back to the margins. If it does not break, the questions get louder. To stay intact under that level of heating and outgassing, 3I Atlas would need to be far more robust than the standard dirty snowball. It could be unusually dense rock. It could be metal-rich. It could have some internal structure that distributes stress more effectively than a random rubble pile. At the extreme end of speculation, it could be engineered to endure exactly this kind of close stellar pass without ever tearing itself apart. Survival alone would not prove technology. Nature can build tough objects, but it would be one more anomaly stacked on top of the others. A hyperactive, carbon dioxide-rich interstellar body with industrial-style nickel chemistry on a suspiciously 14-COP, well-placed orbit that refuses to fracture where many comets would have died would be very hard to wave away as simply business as usual. In the next part, we will follow that speculative thread where it leads. If this really were a craft or a carrier, designed by someone else in a much older era of the galaxy, what would its mission look like, and how well would 3I Atlas match that blueprint? Suppose for a moment that 3I Atlas is not just a frozen leftover from planet formation, but hardware. Not a ship with windows and crew, but a machine built long before our species existed, still drifting through the galaxy on a mission older than our sun. That sounds like pure science fiction. Yet Avi Loeb and a small group of researchers argue that if you look only at the data and ask what a probe would look like, 3I Atlas fits more than one box. Start with mission design. If you were a civilization trying to explore the galaxy, you would not send fragile, short-lived craft. You would build something tough, autonomous, and patient. It might be a large carrier that travels between stars while releasing smaller scouts along the way. Think of it less as a starship and more as a seed. Drop it into a new system, let it taste the environment, deploy tiny devices, then move on. No flashy signals, no obvious beacons. Just quiet sampling over millions or billions of years. 3I Atlas has some of the traits you would want for that kind of job. It appears elongated, possibly cylindrical. Engineers love cylinders. They are efficient shapes for tanks, engines, and spinning habitats because they distribute stress well and pack volume into a compact form. In nature, true cylinders are rare among comets and asteroids. Most are potato-shaped, lumps carved by collisions and slow melting. An honest cylinder makes people sit up. Maybe later images will show that the early reports were wrong and it is just another irregular rock. If they do not, the shape itself becomes a silent argument. Now, think about propulsion and exhaust. That sunward-pointing anti-tail we saw earlier is exactly what a low-thrust engine plume could look like from far away. On a real spacecraft, propellant is expelled in a direction that pushes the craft the other way. If you want to fall inward faster or reshape your orbit, you might fire a plume generally toward the star at certain points. Seen from Earth, that would look like a narrow streak aligned with the sun. In a natural comet, gas vents where heat reaches pockets of ice. In a machine, gas vents where designers bolted the engines. From a distance, both scenarios produce tails. The difference is in control and pattern. Then there is the chemistry. A carbon dioxide-rich flow with water riding along could easily be waste, coolant, or spent propellant. The potential detection of nickel tetracarbonyl suggests metallic nickel in direct contact with carbon monoxide-rich gas in carefully balanced conditions. On Earth, that combination is a refining step, something we do intentionally in factories. In a probe, you could imagine systems that mine, separate, and recycle metals over vast timescales. Iron might be stored in magnetic structures, nickel might be processed and partly vented, leaving the kind of imbalance we see. The activity level at large distance also fits a machine like reading. 3I Atlas should be frozen and quiet in the outer system. Instead, it is alive, outgassing as if energy is being supplied from within. Radioactive decay could provide some of that energy in a natural object, but billions of years of decay eat into that power source. A probe, on the other hand, might carry long-lived power systems, perhaps using radioisotopes or some technology we do not yet know. Its designers could have budgeted energy for repeated perihelion passes, waking systems up whenever it approaches a bright star. Trajectory is another piece. The orbit we discussed earlier, low, inclination, and retrograde, is exactly the kind of path you would choose for a slow, close survey of a planetary system. It brings the craft through the plane where most of the mass and interesting chemistry live. It uses the sun for a gravitational assist. It times perihelion to occur where one of the local technological species happens to have the worst viewing angle. That last part might be coincidence. From a design perspective, though, hiding maneuvers behind a star is just good operational security. All of this leads to a bigger question. If 3I Atlas were a probe, why is it so quiet? Why no obvious radio transmissions? Why no laser flashes or radar pings? Here is where the dark forest idea enters. The dark forest picture imagines the galaxy as a place where every civilization knows that others might exist and might not be friendly. In a dark forest, the safest strategy is to stay silent, to camouflage yourself as part of the landscape, and to watch more than you speak. That idea was born in fiction, but it maps cleanly onto what a cautious explorer would do in real space. In that frame, an interstellar visitor would not advertise itself. It would avoid strong radio beams that might give away its position to anyone listening. It would not carry bright running lights. It would make itself look like a comet or asteroid. Outgassing would resemble normal activity. Tails would point in plausible directions. Any active course corrections would hide inside gravitational accelerations, where they are hardest to detect. From far away, even a nervous young species with telescopes would just check a box that says interstellar rock and move on. Loeb takes this even further. He suggests that if 3I Atlas is a mothership, it may have already done the important part of its job. Smaller probes could have detached long ago, slipping into quiet orbits around planets or moons. They would be too small and too dark to see with our current instruments, especially if they are deliberately built to be hard to spot. The larger body then continues on its path, leaving behind a cloud of watchers. In that scenario, even if we learn tomorrow that 3I Atlas is artificial, it would not mean the real story is still attached to it. There are obvious objections. This is a lot of narrative built on a handful of puzzling measurements. Every piece of the probe picture has a natural competitor. Cylindrical shapes can arise from spin and erosion. Anti-tails can be illusions. Exotic chemistry can emerge in violent star-forming regions. Well-placed orbits can be selection bias. You do not need a galaxy-spanning intelligence to explain any of these things, only patience and statistics. Yet it is also true that if someone had built such probes, this is almost exactly how they would look to us. Old, quiet, embedded in natural processes, hiding in plain sight among comets. That is what makes 3i Atlas such a powerful thought experiment. It forces us to ask whether we are willing to treat the technological hypothesis as one possible explanation to be tested, or whether we still flinch from that idea out of habit and stigma. In the next part, we will step away from alien engineering and look at ourselves instead. How are our institutions handling this object? Why are some scientists eager to talk about its weirdness while others act as if nothing unusual is happening at all? The answers say as much about human nature as they do about any visitor from the stars. While all of this is unfolding in space, something just as revealing is happening on the ground. The data on 3i Atlas is strange, even by Comet standards. Yet if you look at official statements from major agencies, the tone is calm, almost sleepy. NASA calls it a natural interstellar comet. The European Space Agency calls it a valuable target. No one with institutional authority is standing at a podium saying this might be a probe. The loudest voice, even, hinting at that possibility is still Avi Loeb. That gap between what the numbers suggest and what most scientists are willing to say in public is its own kind of anomaly. Part of this comes down to how science is supposed to work. The culture of astronomy is cautious by design. You do not claim something extraordinary unless you have evidence so strong that even your harshest critics have to nod slowly and say yes. That cautious attitude is the reason we trust scientific results. It is also the reason most anomalies are quietly filed away as measurement errors or rare natural events, never as signs of something outside the current playbook. There is a long history of this reflex. For decades, reports of ball lightning were brushed off as illusions or folklore because they did not fit existing models of electricity in the atmosphere. Fast radio bursts were dismissed as interference from microwave ovens and faulty cables, before careful work proved they were real, powerful flashes from other galaxies. In each case, strange data arrived, the community resisted, and only after repeated confirmation did the official story change. That pattern is not villainy, it is inertia. Paradigms do not like to move. 3i Atlas has walked into that same machine. On paper, it has an anti-tail that seems to defy basic comet geometry. Water boiling off at 3 astronomical units, an 8-to-1 ratio of carbon dioxide to water, nickel-rich outgassing with little iron, possible industrial-style nickel compounds, and a low-inclination retrograde orbit with a tiny natural probability. That stack of oddities is exactly what you would expect to generate loud debate. Instead, much of the mainstream response has been a shrug and a footnote: Interstellar Comet. Interesting. Next, if you talk to comet specialists, many will tell you that nothing here requires a new category. Anti-tails have been seen before, often explained by dust sheets and viewing angles. Exotic chemistries are common in a universe where stars live and die in violent ways. Selection effects can make rare orbits seem special. From that point of view, 3i Atlas is not a crisis. It is just data that has not yet been fully digested. Why fan public speculation when patience will probably flatten the story? Loeb pushes back on that comfort. He argues that when you see multiple anomalies in a single object, the responsible thing is not to throw each one into a separate drawer labeled rare but natural. It is to ask if they might share a common cause. He also points to something more uncomfortable. The stigma around taking extraterrestrial technology seriously has been so strong for so long that many scientists will do almost anything to avoid being associated with that topic. Funding panels frown, colleagues whisper. Careers bend quietly away from the word artificial. You can see that tension in the way searches are organized. Most of the telescope time devoted to 3i Atlas goes into classical comet science, high-resolution spectra to refine chemical models, imaging campaigns to study dust dynamics, orbital refinements to test non-gravitational accelerations. All of that is important. Hidden in the background, a few teams are also running machine learning on light curves, searching for unnatural patterns and scanning for spectral lines that do not match any known molecule. Those efforts are small, often underfunded side projects rather than central missions. Even the search for extraterrestrial intelligence reflects this divide. Facilities associated with projects like Breakthrough Listen have pointed their antennas at 3i Atlas across multiple radio bands. So far, nothing clearly artificial has appeared. No narrow band beacons, no repetitive coded bursts. Officially, that is reported as a null result, and the subject moves on. Loeb and others remind us that silence on those channels only tells us one thing. If this object is a machine, it is not chatting, in ways we know how to hear. Beyond that, the data are agnostic. Then there is the institutional need to project calm. Space agencies answer not just to scientists but to governments and the public. Declaring that a visiting object might be technological opens doors to questions those institutions are not ready to manage. Is it dangerous? Are we being watched? Are we being lied to? It is far safer, politically and psychologically, to emphasize that there is no threat, no evidence of control, no reason to panic. Official narratives are shaped as much by social stability as by raw evidence. Avi Loeb sits in a strange place inside this ecosystem. He is not an outsider with no training. He is a former chair of a major university department with hundreds of peer-reviewed papers. When he argues that we should treat artificial origin as a testable scientific hypothesis, he does so from inside the establishment. That is exactly why the pushback is so sharp. Some accuse him of chasing headlines. Others say he is eroding public trust by mixing speculation with data. Loeb replies that refusing to explore certain explanations for fear of ridicule is the opposite of scientific courage. In a sense, 3i Atlas has become a mirror. On one side, you have a conservative culture that worries about being wrong in an embarrassing way. On the other, you have a minority that worries more about missing something enormous because we were too proud or too scared to look. The object itself does not care. It follows its path, sheds its gas, and reflects sunlight in whatever way its structure allows. We are the ones turning those photons into stories about what is possible and what is allowed. In the next part, we will flip the table and assume the conservative view is right. We will imagine that every anomaly finds a natural explanation, that 3i Atlas really is only a comet. Then we will ask a different question. Even if it is just ice and rock from another sun, how much does that still change our picture of the galaxy and our place inside it? Now, let us flip the script completely. Forget probes, motherships, and stealth missions. Imagine that every strange feature of 3i Atlas eventually finds a natural explanation. The anti-tail turns out to be an illusion of dust and perspective. The nickel chemistry is traced to some exotic but still natural mineral mix. The orbit falls neatly into the category of rare paths that statistics say must happen eventually. In that world, 3i Atlas is only a comet. The question then becomes this: how much does that still shake what we thought we knew about the universe? We already have a useful comparison in Borisov, the second interstellar object ever seen. When astronomers studied Borisov in 2019, its behavior and composition looked surprisingly familiar. It resembled comets from our own distant cloud of icy bodies. That result was comforting. It suggested that building comets might be a fairly universal process. Different stars, similar leftovers. 3i Atlas has already broken that illusion. Its carbon dioxide heavy mix, hyperactive water at great distance, and possible industrial-style compounds tell us that interstellar comets are not all copies of our own. They can carry wildly different recipes. Even if everything about 3i Atlas is natural, it is still a direct sample from another planetary nursery. The carbon and oxygen balance in its ices record the chemistry of a star that is not our sun. The extreme ratio of carbon dioxide to water says that in some systems, hydrogen is scarcer or trapped in different ways. That single fact forces modelers to widen their view of planet formation. It means there are worlds where water-rich bodies like ours are not the default outcome. Carbon-rich, water-poor systems may be common. Isotope ratios would sharpen that picture even further. The relative amounts of different versions of carbon, oxygen, and Other elements act like a barcode for the cloud that birthed this object. If we manage to measure those ratios accurately, they will confirm not just that 3I Atlas is interstellar, but what kind of stellar neighborhood it came from. If the ratios are very different from those in our system, they will prove that the galaxy is chemically patchy in ways we have only modeled on paper. If they are similar, that is just as interesting. It hints that certain chemical patterns might be favored across many star-forming regions. Either way, the comet becomes a messenger from a place we will never visit. Even its age matters in the natural case. Models suggest that 3I Atlas could be 7 to 10 billion years old. That is older than our Sun by several billion years. A natural object that, ancient, still active, still shedding mass, shows that the galaxy can preserve icy bodies for almost the entire history of stars. It has survived close calls with other stars, passages through violent regions filled with radiation, and the slow grind of time. Yet here it is, still able to flare with gas and dust when warmed. That endurance alone expands our sense of how long the debris of planet formation can remain intact. Now, fold in the way it behaves. The water at 3 astronomical units, the strong outgassing in the cold, the nickel-rich vapor, all have to be folded into new models of comet physics. If these effects come entirely from natural causes, then the physical processes we use to describe how icy bodies warm, crack, and vent are incomplete. Energy sources we thought were negligible at large distance must be re-examined. Volatile mixes that we treated as secondary might become central in certain environments. In other words, the laws do not change, but the ways they combine do, and our simplified mental picture of comets needs a serious upgrade. There is also the broader statistical lesson. We have found only 3 interstellar objects in roughly 8 years. 3I Atlas is the third, and it is already far stranger than anyone expected. If this is what we see in such a tiny sample, what does the full population look like? Theoretical work suggests there should be thousands of such visitors passing through the inner solar system at any given time, most too small or too dim to notice. If even a small fraction of them are as chemically extreme as 3I Atlas, then our solar system is not a standard template. It is just one flavor in a vast cosmic menu. All of that matters, even if no one ever utters the word artificial again. A purely natural 3I Atlas still forces astronomers to design better surveys, more sensitive instruments, and faster response plans. The missed opportunities with Oumuamua and the limited window on this object have already sparked serious conversations about rapid mission concepts. Small probes that can launch on short notice, intercept an interstellar visitor, and sample its chemistry up close are no longer science fiction. They are engineering problems waiting for political will. For the rest of us, a natural verdict does not make the story dull. It means that the universe is capable of building ice rocks older than our star, with chemistries that look almost industrial, throwing them across the galaxy, and occasionally letting them pass through our sky. It means that when we talk about the diversity of planetary systems, we are not just speculating. We are reading actual fragments of those systems as they drift by. In that sense, the conservative outcome is still radical. If 3I Atlas fragments are perihelion, and every anomaly falls into place inside expanded comet theory, it will not have been a disappointment. It will have been a teacher that forced us to admit how narrow our view of comets and star systems really was. And it will have set the stage for the next interstellar object, which will arrive to a community far more prepared to catch every photon and every clue. In the next part, we will return to the wilder branch of the decision tree. We will imagine what happens if the evidence refuses to fit inside the comet box, and how science, governments, and ordinary people might react if 3I Atlas forces us to admit that something out there is not just natural rock and ice. Now walk down the other branch of the tree. Imagine that the data do not cooperate with the safe story. The object sweeps through perihelion and does not fragment. High-resolution images from different observatories agree that its shape is truly cylindrical or shows repeating geometry that nature almost never produces. Velocity measurements reveal changes that cannot be explained by any realistic pattern of outgassing. Spectra show lines that match no known mineral and hint at structured materials. At some point, quietly at first, a sentence appears in a technical paper that says, "Natural explanations are insufficient." What happens then? The first shock would hit the astronomical community itself. Overnight, 3I Atlas would shift from being a curious comet to the most important object ever studied. Telescope schedules around the world would be torn up and rewritten. Projects that had waited years for observing time would be pushed aside so that every suitable instrument could stare at this one point of light. Data pipelines would be reconfigured. Teams that once treated this as side work would suddenly find themselves at the center of a global rush. Space agencies would convene emergency working groups. Panels would form that mix: dynamicists, spectroscopists, engineers, and philosophers who think about the search for extraterrestrial intelligence. Their job would not be to shout "alien" on television. It would be to test and retest every alternative natural explanation, to push the models until they break, and to decide what level of confidence is required before anyone uses the word technological in an official statement. The tone would be careful, hedged, and very tense. Governments would not sit this one out. Intelligence agencies already operate powerful sensors that watch space for missiles and other threats. Many of those instruments can be repurposed to track small objects. If 3I Atlas looked artificial, those classified systems would almost certainly be pointed at it. Some of that data might never see the public. Instead, filtered summaries would move up chains of command. Questions would multiply. Is it under control? Could it alter course toward Earth? Does it carry anything that might threaten satellites or infrastructure? Even if the scientific answer is that it is harmless, the security apparatus would need to check. In the media, the story would detonate. The headlines would rotate between awe and fear. Confirmed evidence of extraterrestrial technology, humanity no longer alone, first visitor from another civilization. Talk shows would fill with experts and non-experts arguing over what it means. Some would insist that this changes everything. Some would say that nothing in daily life will shift right away. Conspiracy theories would explode as well. Accusations of cover-ups, secret contacts, hidden messages. The online world would become a chaotic echo chamber. For most people, the deeper impact would take longer to sink in. There would be no voice from the object, no landing, no exchange of greetings. It would remain a distant, silent thing, gliding past the sun and heading back out into the dark. That distance would make the discovery feel strangely abstract. You would still go to work, still make dinner, still pay bills. Yet somewhere underneath, a pillar of the old mental model would have cracked. For the first time, the sentence "we are alone" would be false in a concrete way. Philosophy and religion would wrestle with the news. Traditions that place humanity at the unique center of creation would have to reinterpret what uniqueness really means. Thinkers who have long argued that intelligence is a natural outcome of cosmic evolution would feel vindicated, but also humbled. We would be forced to admit that another culture mastered interstellar travel while our planet was still a young, lifeless rock. In the cosmic timeline, we are not the pioneers. We are the late arrivals discovering that someone else passed through long ago. Within science, whole new disciplines would bloom. There would be a rush to read every possible signal from the artifact. The exact geometry of its surface might reveal design principles. The way it outgasses might hint at power systems or internal reservoirs. If any fragment could be recovered or sampled, even as dust in its trail, laboratories would scrutinize it atom by atom. We would be doing archaeology at interstellar distance, piecing together a culture from a single passing machine. The ethics of response would also become real. Even if the object is not transmitting, some will argue that we should send a parter, message toward its path, a directed radio or laser signal that says "we saw you." Others will argue fiercely against that, warning that broadcasting our presence to unknown listeners is reckless. The debate over messaging extraterrestrial intelligence, which has lived in academic circles for decades, would spill into public policy. For the first time, it would not be a hypothetical. It would be a live choice. There is a darker possibility as well. Evidence of a probe says that at least one other civilization existed. It does not say whether they still exist. 3I Atlas could be a relic from a culture long dead, still executing a program it was given billions of years ago. In that case, the discovery would be both thrilling and tragic. We would know we are not a unique outcome, but we would also know that even spacefaring societies can vanish, leaving only silent machines. That thought would hang over our own future like a quiet warning. And after the object fades, what then? The telescopes will turn back to other targets. The news cycle will move on, yet the baseline of human understanding will have shifted. Every child born after that moment will grow up in a world where extraterrestrial technology is not speculation but historical fact. Curriculum, culture, and even casual conversation would slowly adjust. Our maps of the universe would now include not just galaxies and nebulae, but evidence that minds elsewhere have acted on the cosmos. In the final part, we will step back from both extremes and return to the present moment, where the outcome is still unknown. We will ask what signs are worth watching, how amateurs and professionals together are tracking this visitor, and what the legacy of 3i Atlas will be, no matter which way the verdict finally falls. Right now, as you hear this, 3i Atlas is still out there, carving its path through the inner solar system. The models have been run, the simulations are humming on supercomputers, the arguments are already in full swing, yet the universe has not given its final answer. We are in the quiet, electric space before the reveal, where every new data point could tilt the story toward ordinary comet or something far stranger. This is the part of the story where watching closely matters. So, what should we actually look for? The simplest sign is fragmentation. If 3i Atlas approaches the Sun and splits, if we start seeing multiple bright knots where there used to be one, that is a powerful vote for the natural comet camp. You would expect a flare in brightness as fresh surfaces are exposed, then a gradual fading as the fragments drift apart and lose activity. In that scenario, the object that sparked so much speculation dies the same way many comets have died before, in a flash of fragile ice and dust. If it does not break, the next thing to watch is its path. Orbital predictions right now are accurate enough that even small deviations will stand out. After perihelion, careful measurements of position and speed will show whether the actual track matches what gravity and measured outgassing alone can explain. If the path stays within the narrow corridor that standard models allow, the arguments for active control become weaker. If it drifts outside that corridor in a way that cannot be reconciled with natural forces, then the quiet question is going to get much louder. Spectroscopy is another key. As the object swings in close, its coma will glow brighter, and more molecules will reveal their fingerprints in the light. New emission lines may appear. Some will match known substances and refine our understanding of its composition. Others might not match anything in existing catalogues. Unidentified lines are not proof of technology. They are proof that we are still learning the chemistry of the galaxy. Yet, if those lines hint at ordered structures or complex metal-organic compounds, the debate will sharpen. Structural hints will come from the best images we can get. Earth-based telescopes with adaptive optics, space-based observatories, and the JUICE spacecraft all offer different vantage points. None will see a crisp science fiction silhouette. At these distances, even our sharpest views will look like soft blobs with subtle elongation. Still, changes in brightness as the object rotates can reveal whether it is roughly spherical, potato-shaped, or truly elongated in a way that points toward a cylinder or a flattened slab. Any repeating patterns that track with rotation would be especially interesting. Brightness itself carries clues. Astronomers are already tracking how the light from 3i Atlas rises and falls as it approaches the Sun. Some of that change is simple geometry. Closer objects look brighter. Some of it is activity. More gas and dust means more reflected light. If the brightness curve follows well-understood patterns, it reassures the conservative models. If it flickers in ways that are out of sync with distance, rotation, or known jets, it suggests something more complicated is happening inside. While all of this unfolds, a second story is playing out on Earth. Amateur astronomers are turning their telescopes toward this visitor whenever the skies and the sun's glare allow. Many are capturing images that, while less precise than professional data, fill in gaps in time and coverage. Citizen scientists are downloading public survey frames, stacking them, and hunting for subtle changes. Forums, Social media threads and comment sections are buzzing with people who, for the first time in their lives, are following an interstellar object day by day. That attention matters. It keeps pressure on institutions to share data openly and quickly. It pushes journalists to cover nuance rather than dismissal. It nudges space agencies toward considering rapid response missions for the next visitor. Even if most of the wild theories are wrong, the energy they generate helps fund the very instruments that will eventually give us right answers. Curiosity, even messy curiosity, is fuel. Whatever verdict the data eventually deliver, the legacy of 3i Atlas is already forming. It has forced Comet scientists to stretch their models to include extreme carbon dioxide-rich bodies that become active in the cold and carry metals in odd states. It has forced dynamicists to think harder about interstellar trajectories and how selection bias shapes what we see. It has pushed the search for extraterrestrial intelligence community to include passing rocks and ice bodies in their watch lists, not just distant stars with planets. It has also tested our collective willingness to entertain big questions without losing our grip on evidence. On one side, there is the temptation to leap straight to aliens at the first whiff of weirdness. On the other, there is the temptation to shove every anomaly into a drawer labeled noise. 3i Atlas is a challenge to both instincts. It asks, with us to walk a narrower path, where we admit that technology is one possible explanation for strange data, but insist that it earn its place in our models the same way any hypothesis must, by surviving hard, repeated tests. In the longer view, this object is not the end of anything. It is the beginning of a new era in which interstellar visitors are no longer rare curiosities. As surveys grow more sensitive and all sky monitors more powerful, we will spot more of these travelers. Some will look like Borisov, comfortably familiar. Some will look like 3i Atlas, chemically or dynamically strange. Statistically, if other civilizations exist and build durable machines, at least one of those future visitors may one day refuse to fit any natural pattern at all. When that day comes, we will be better prepared because of this one. We will have practiced the art of rapid observation. We will have built the tools to launch fast probes. We will have rehearsed the conversation about how to talk to the public and to one another when the universe hands us something that upends old assumptions. 3i Atlas, whether it is a comet or a craft, is training us. It is teaching us to be a species that pays attention when the cosmos sends something small, bright, and inexplicable through our sky. And maybe that is the most important part. Not whether this particular visitor is natural or artificial, but what it draws out of us. More careful science, more open minds, more eyes turned upward. A deeper sense that we live in a galaxy full of stories still waiting to be told, carried on tiny, icy messengers from suns we will never see up close.